So this is changes within a small population, and including the founder effect. But first, small populations have a smaller, clearly have a smaller gene pool. So small populations, that's my small population, always has a smaller gene pool. Right. So with the smaller gene pool, this has lesser the smaller gene pool has a lesser genetic diversity, with less genes and less alleles with the lesser combinations. So less genetic diversity. Right. With a large population, on the other hand, there's a larger gene pool. The alleles have greater genetic diversity, and it would lead into variation within the population, which is more important in natural selection. For the selection pressures, such as disease, prey, competition, or human influence. So if I just recap the selection pressures. So, selection pressures. These include prey, the amount of food available, competition. Competition includes habitat, mating, food, sunlight if you're a plant, diseases is very common, and human influence. So these are the selection pressures that can change and alter the environment, which would then again change the gene pool. Human influence. So, small populations, like we see here, with limited genetic diversity cannot adapt and change as easily as large populations can, and therefore these smaller populations with the smaller gene pools are more likely to become extinct and vulnerable. So the strain of the pathogen, for example, if you have a disease, may wipe out an entire population if it's small and got restricted genetic diversity with lesser. That's the same with inbreeding. It has lesser genetic diversity, smaller gene pool, more likely to all be affected by the same disease or characteristic from the environment. So what can the size of a population be influenced by? So the population in the gene pool, how can that be influenced? So there's density dependent. So density dependent. Density dependent is something that's dependent on the population size. So this is competition. These are the selection pressures up here. So competition is density dependent. So is predation. They're very linked, predation and competition. Parasitism. Can't really say that very well. And communicable diseases. Disease. So this is everything that's related to having grouped together. So if you have a large group, if you have a smaller group, that's quite density dependent on communicable disease, as they, like I said, they can all be affected by the same genes. Parasites can be transferred a lot easier if you're in a larger group, in a big group together, or actually be more resistant in a big group. Predation, you're more likely to be bounced back from it if you're in a bigger group, and same with competition. But if there's more competition with greater numbers of organisms, there's more likely to be less food, so there's going to be greater competition if you're in a bigger group. So there's it depends what, if you've got a small, you just have to kind of be logical. And then you also have density independent as the other one. So density independent. Density independent can affect any size population. So these are the more external factors that donate to the selection pressures. So this is the ones that are climate change, climate change, so natural disasters, and even seasons, things that the doesn't matter how much you have of. Well, it might limit your competition with habitat, etc. What the resources are left, but this is predominantly density independent because it's not completely reliant on the dependent. While you can fit them in both categories, and then finally human influence. While these limit this natural disasters, climate change, seasons, all limit the competition and predation, this is where it comes from, so that's density independent. Right, so these problems can be described as a population bottleneck. So a population bottleneck, if I do a little diagram here, like that. So this is the gene pool, and the genetic diversity are reduced, and the effects are seen in the future. So, say you have a gene, this is your gene pool, this is your population, these are all the different alleles, the different variation of alleles. So you have quite a lot of variety, so you have, it's quite a big population, have a lot of variety in there. All the colours represent different types of alleles. So that's all the variety in your current pre-disaster habitat. So there's all the different ones in the environment. It's all of them. So that's quite good, quite healthy. Got a lot of genetic diversity. That's quite good, quite stable. So, and then you have a density independent problem. We have an epidemic. So here, this is here is the event or the disaster, or the epidemic, depends what it is, disaster, this is what that is. So it's greatly reduced, the population is extremely reduced, so if you have a disease and then they all get affected and a lot of them die. So that would also mean, on the other side, the alleles are greatly reduced. The variation is greatly reduced. So while it does level out with the same amount at the end, it does reduce the diversity extremely. So the gene pool and the genetic diversity are reduced, as you can see here, seen in the future. But this does take a very, very, very long time to actually see the lack of genetic diversity to develop through the slow mutations. For example, cheetahs have had trouble inbreeding, and therefore they have had reduced fertility. This is called the founder effect. And the founder's effect is when small populations are formed by isolated individuals in a larger gene pool. So, the founder effect is actually small populations, so this little small population here, is formed by isolated individuals. So I'll put a little individual in the little box, little man. Founder effect is by an isolated individual from a larger gene pool. So this is what's happening here. This is the larger gene pool, been isolated somehow, whatever the epidemic or disaster was isolated, and then not divides, but reproduces, but this really extremely limits the genetic diversity on the other side of the founder effect. But it's very important that this is isolated. They're isolated here for the founder effect. The extreme example of genetic drift. So, for example, an extreme example is Amish people is something called polydactyl, which is an extra finger or toes, and that was caused by one couple alone. This was caused by only one couple, and they reproduced, so they were here because they were limited, and they kept reproducing, and obviously their alleles spread, and they have less genetic diversity, so Amish people are quite common to have the disease. And these characteristics can be seen on a graph of population. So these characteristics can be seen on a graph. So if you have, this is called a stabilizing selection. So this is a normal distribution, and you have number of individuals up here, and you have variation down here. Normal distribution will commonly be seen like, well, that's bad, like that. That is a normal distribution. This is called a bell-shaped curve, as you can see from the sort of shape of it. It's called a bell-shaped curve. And it looks like this, yeah, about. So this is a normal distribution. You can have, for example, the birth weight of babies. So if a baby is too light, so down here, if the babies here are too light, they're quite prone to infections. So their chances of survival are reduced. That's the same for the larger sized individual. The larger sized baby are quite also hard to survive, basically. So the most common is the average between them, so that it has a greater chance of survival. That's why it's most commonly